My name is Takuro Shinano. I'm from the Hokkaido University. But actually, I've been working on the remediation of the contaminated agriculture field in Fukushima Prefecture after the FDNBD accident for 6 years here. And after that, I'm still working on the remediation process by working with some colleagues in Fukushima Prefecture also. And today, I'm going to talk about the importance of the exchangeable 137 cesium to predict plant radioactivity. And previous presentators have mentioned that after 11 years and 7 months, the affected area of the radioactive cesium contamination is decreasing. The middle figure shows the restriction area for the crop production in 2012. And the right figure shows the restriction area this year, 2022. And only difficult return zone is still remaining for the restriction area for the agricultural activity. And this decrease of the restriction area was carried out mainly by the physical decay of the radioactive nuclides, and also, as Wakiyama-sensei mentioned, that the contamination process is also one of the very important processes, especially for the agriculture field. The government have decided to apply the topsoil stripping by using such kind of construction machines. And after that, non-contaminated mountainous soils are dressed and mixed again to reduce the radioactivity of the soil. But of course, this procedure produced a huge amount of the contaminated soil. And this is one of the problems. And but I'm not talking about how the fate of these contaminated soil today. And the other problem is that this topsoil stripping method cannot reduce all the radioactive cesium from the soil, because this figure shows that one of the instructions for the Ministry of Environment to how to do the decontamination, physical decontamination, topsoil stripping for the to the workers. That means that you may know that actual field is not flat. There's such kind of the hill, and you cannot take equally at the depth of 5 centimeters. So it means that some substantial amount of radioactive cesium is still contained after the decontamination process. Like in the some areas in the difficulty turning zone, sometimes it is about 5,000 becquerel per kilogram, even after the decontamination process, even after the mixing the non-contaminated soil up to 15 centimeter depth. So it is also required to apply another remediation technique. That is one of the important points is that applying the potassium fertilizer to reduce the radioactive cesium transfer from the soil to the plant. And this is one of the examples of the soybean case. And as you can see that when the soil exchangeable potassium level increases, the transfer factor is one of the parameters to explain how the radioactive cesium move from the soil to plant. And it is clearly shown that soil exchangeable potassium level is pretty important to regulate the transfer factor. And based on this, the Japanese government started to apply a huge amount of potassium fertilizer to the field. However, there is some difficulty to consider how to manage the potassium application to the soil. One is the difference is existed between the exchangeable potassium level and the transfer factor among the crop species. Like in rice, the left one, compared to rice plants, those soybean and buckwheat shows a higher transfer factor. In this case, it is written in concentration ratio, but it is pretty same to the transfer factor. And the soybean and buckwheat shows a higher transfer factor at the same exchangeable potassium level as shown in this figure. But I'm not going to talk about this problem today. I'd like to mention that the other problem of soy. As Fukushima Prefecture, the Minister of Agriculture and Fishery and Forestry and Fishery has been doing the monitoring survey from the 2012 to until now. And using the, in this case, we have used more than 500 different fields, and not so different, I'm sorry, not different, 500 fields. And we used those data of the, this case is a paddy field, and we analyzed the soil radioactivity and several physical chemical property of the soil, and also the brown rice radioactivity. And we calculated transfer factor, and we plotted it against the exchangeable potassium level of the soil. And it is shown that in Nakadori, it is written in red dot here, show the lower transfer factor at the same exchangeable potassium level as shown here, when compared to the Aizu or Hamadori. And brown rice radioactivity can be determined by the multiplying soil radioactivity and transfer factor. And fortunately, in Aizu prefecture, not prefecture, Aizu area, the contamination level is pretty low. So the risk is also low, even though the transfer factor is high. But in the Hamadori, as Fukushima Daiichi FDNPP is located in the Hamadori, and also the most of the difficult return zone is still existing in the Hamadori, which means that the radioactivity of the soil is pretty high. And as I mentioned, that even after the decontamination process, the radioactivity still existed. So we should think about the difficulty of the Hamadori. So we have carried out some experiments, not only for rice. In this case, we collected soil from the Nakadori and the Hamadori, and we use komatsuna. Komatsuna is one of the very famous Japanese leafy vegetable, brassica. And we calculate, we plotted those komatsuna on the pot experiment in the same greenhouse. The radioactivity of the soil was almost similar, about 1,300 becquerel per kilogram. And we applied different level potassium application, and we changed the exchange potassium level as shown here. And by using this data, it is clearly shown that the radioactivity of komatsuna is pretty different between these soils. In this case, also, the soil from the Hamadori shows higher radioactivity at the same exchange of potassium level. And we also carried out some experiment by using the soybean plant, using the two fields. One is Nakadori and one is Hamadori. And this is the result of the transfer factor and the exchange of potassium level. And in this case also, from the sample of the Hamadori, it seems that transfer factor is higher than that of the Nakadori when compared to the same exchange of potassium level as shown here. But this result is very important to consider the mediation of the agriculture, because we need to stand the safer side. I mean, if we want to control the transfer factor lower than 0.05, we must put the level of exchange of potassium level is in this case about 20 milligram potassium oxide per 100 gram, not 10. Because so we need to find out more sophisticated way to to predict how the plant absorbed radioactive cesium from the soil. So we introduced the analysis of the exchangeable 137 cesium, as Haya-sensei mentioned also. And by using 137 exchangeable 137 cesium concentration in soil, we designate some other equation very similar to that of the transfer factor. Transfer factor is 137 cesium concentration in plant divided by the total 137 cesium concentration in soil. But we designate it as CR exchangeable 137 cesium, as shown in the lower one. But in this case, the 137 cesium concentration in the plant divided by the exchangeable 137 cesium concentration in the soil. And by using this equation, the light figure can be shown that the difference between the soil was very small. And we can use this method to predict how the plant accumulates radioactivity from the different soil also. And the importance of the exchangeable 137 cesium has been mentioned by other researchers also, such as by Kondo et al. In 2015. And he has mentioned that if when the exchangeable 137 cesium concentration power exchangeable potassium is high, the concentration of the plant, in this case, rice plant, become high. And also, Yagasaki et al. In 2019, he has also mentioned that when the exchangeable radioactive cesium concentration, and this, here, if the is higher than 500 becquerel per kilogram, the brown rice radioactive cesium concentration is high. And these results indicate that the exchangeable 137 cesium concentration is very important to consider about how the plant uptake 137 cesium from the soil. From the physiological point of view, radioactive cesium uptake is analyzed by the European researchers before the Fukushima accident. And they have found that the ratio of the cesium and potassium is very important to regulate the cesium uptake by the plant. And they have designated a shear concentration factor. And it is true because the plant cannot directly absorb nutrients from the soil. They need to absorb them by the ion state. So, but in the urgent condition, taking soil solution, especially from the upland soil, is very difficult, and the analysis takes a pretty long time. So, actually, transfer factor was used even after the Chernobyl condition and also the FDNPP condition. And we found that exchangeable potassium level is very important to regulate the transfer factor. But as I mentioned, that there is some difference among the soil. So if thinking about this, exchangeable potassium is one of the indicators to explain how the soil can supply potassium ion to soil solution. And it is same for the exchangeable 137 cesium. This is the potential of the soil that can supply 137 cesium ion to the soil solution. So using this CR exchangeable 137 cesium is a very good indicator, and it is better to use instead of the transfer factor, I think. That's the conclusion. Thank you very much.
Thank you very much, Shinano-sensei. There are questions. That's your hands.
Thank you very much for a very interesting talk. You sort of mentioned it rapidly, but maybe I missed it. What is the importance of the farming practices from farm to farm and from field to field on the potassium intake?
Actually, not actually. You mean that agriculture practice for the remediation?
Practices by each family on its field and.
Actually, it is there is some conventional method to apply the conventional amount of potassium, like in the case of potassium application for each crop and each field. But actually, to remediate the radiation, the government has decided to use additional amount of potassium for the conventional amount of potassium. So in some cities, the government put the potassium fertilizer in each field to apply before or after the conventional one. That is a method, a practical analysis, practical usage of the remediation technique.
Thank you very much for your presentation. It is very important for the predicting the concentration of session in the crop for the futures. Then I have questions. What is the session concentration in crops depends on the potassium, but the applied potassium is very, very different, depends on the area. Some is, for instance, the homemade ground is very low, and some is very high. So the more realistic estimation is needed every time measuring potassium. Is that right?
Yeah, actually, based on the equation, it is true. But I think that it is not practical. And we are now thinking that I think that maybe in this year, one paper will be published by the by Eguchi-san and other researchers from France and Vienna, and they have some information that they can directly estimate the amount of potassium. I mean that the exchangeable potassium level by using the FTIR or mid-range IR technique. I'm not completely sure, but they have said that, and by using those data, those analysis, very quickly analysis of the soil, just checking the soil surface analysis, and they can estimate the amount of exchangeable potassium level. So by using those techniques, I think it's possible to apply a very analysis will be very easy, and how to say, the two-dimensional analysis can be carried out for the future analysis. Yeah, actually, but at this time, that practical application of this such kind of equation is pretty difficult, because we should be more safe. I mean that we should stand for the safer side to determine the amount of the potassium application level. Yes, I understand your question. Yes.